Let's talk about what map projections are. So the idea behind map projections is we're taking a globe, which is an ellipsoid, which is this round thing, and we're trying to put it onto a flat surface so that we can make a map of it. And this kind of shows like if the Earth were a beach ball and we took that beach ball and cut it into pieces, it would kind of flatten out, but still there would be some bumps and irregularities associated with it. And the map projections take care of these things mathematically. Maybe another way to think of a map projection is let's start, instead of the entire globe or the entire Earth, let's just take half of a globe that's maybe made of glass, and the outside of that glass is painted with where the continents are and maybe some lines of latitude and longitude. And let's put a light bulb in the center of that. So there are if we put a light bulb in the center of that and then just projected that light through the globe and onto a flat wall, we would see a map of what the Earth would look like if we did one of these things called a map projection. That would be called an azimuthal or planar map projection. And we can obviously project something onto a flat plane, and then we have something like a flat map. But we could take a piece of curved paper, like half of a cylinder, still put the light in the middle, project that light onto the cylinder, draw out where all the continents and lines of latitude or longitude are, and then take that half of a cylinder and flatten it out onto a flat surface. And that would also give us a map projection. There's one other surface we can do this with, and that's a cone. With a cone, we can either place it, in this case, over the North Pole or the South Pole, but in this case, the North Pole, the cone is going to touch the Earth in a certain place, but regardless, that light is going to take all that information on half of a globe and project it onto a cone, and then we can take that cone and we can flatten it out into a flat piece of paper. All three of those are examples of how map projections work. But when we project a round globe onto a flat surface, we're going to have distortion. There's just no way around this. There's always going to be some sort of distortion. But sometimes we can make it so there's no distortion in distance or direction or shape or area, but not all of those things. So we kind of choose what kind of distortion we want to show on a flat map of the globe. Another thing we can do is, as you see, there's in this example here, there's several different map projections. Each one of these little slices would be a map projection, and there's space in between. We would call that an interrupted map projection, and we're trying to decrease the distortion by not requiring these map projections to be stretched out to fill in all this empty white space in between. So that would be how we can interrupt map projections in order to decrease the distortion. So let's look at some specific examples here. This is a map of the Earth from above. Here's the North Pole here. And if we were looking at what direction anything on the map was from the North Pole, there would be no distortion in direction. We could just go along this line of longitude and you will get to the point that you need to get to, depending on where you want to get on the surface of the Earth. For example, Greenwich, England, you would just follow the prime meridian straight down here until you get to Greenwich, England, and the direction is not distorted. But what if we wanted to show a map where the distances were correct? Well, this is a very different map. Now we're no longer just showing the northern hemisphere. In fact, here is the line of the equator here, this red line here, and we're showing the entire Earth on a map projection. So things have obviously been distorted here. The shape of things are distorted. That's not really what Australia looks like. But the one thing that's good about this map is we can measure the proper distance from the North Pole to any point on this map projection. So we're seeing the distortion, but for purposes of measuring distance from the North Pole, this is an excellent map projection. This is something called an orthographic map projection. orthographic, orthographic. And it's how we would see the Earth from space. So if we were up in a satellite, it's a distorted view of the Earth, right? These lines of longitude, for example, are getting closer as we move towards the edge of the map. But it is a view we're used to because it's what the Earth would look like from a spaceship that was floating above the Earth. So these orthographic map projections can be very useful because they show us what we're used to seeing. However, in this map projection, we can only see half of the Earth at once. Of course, we could put the other half of the Earth right next to it and show the entire Earth at once, but that's one of the options with orthographic map projections. This is a different map projection. This is called a Mercator map projection, M-E-R-C-A-T-O-R map projection. And this is showing all the continents on the Earth the proper shape. So the shape is not distorted. And another nice thing about this is the direction is not distorted. So sailors often use this map. If you were trying to sail from Spain over to the New World and you have this sort of map on your ship, you could just measure an angle of where you wanted to go, head off on that bearing, and if you were able to keep constant on that bearing, you would end up where you wanted to be. So these can also, in addition to not distorting shape, they can show lines of constant bearing. However, the Mercator projection has gotten some really bad press because it makes things in the northern hemisphere, like the United States and Europe, look much larger than they really are. For example, Greenland is not really larger than the continent of Africa. But in not distorting the shape of the continents, this map projection actually distorts the area a lot. So could we make a map of the world with the proper area? Well, sure. Here's one example here. Most people, when they first look at this, do not think it looks as natural as the Mercator because we're so used to seeing the Mercator. But this is a equal area map projection. It's called the Peters map projection, P-E-T-E-R-S. And this was created by someone, actually recreated from an earlier map projection that shows all the continents in their proper size. And now we can see that Greenland is in fact much, much smaller than Africa. We can see that the way that they've done this is they brought the lines of latitude closer and closer together as we approach the North Pole and the South Pole to account for the distance between the lines of longitude getting shorter and shorter. So this Peters map projection, it does show the true size of things, but there's plenty of other ways to show the true size of things in a map projection. This is an equal Earth, E-Q-U-A-L space E-A-R-T-H map projection, and it's showing all of the continents on the Earth at the proper size, but it doesn't look to us as distorted as to most people as distorted as the Peters map projection. And the people that created this map projection have done this in a number of ways, but we can see it's different than the Peters in that the lines of longitude are starting to converge. They're coming together near the North Pole and the South Pole, but those distances between the lines of latitude are also getting lesser and lesser as we move in this direction here. So plenty of different map projections out there. They're all trying to show the round globe or the ellipsoidal globe on a flat Earth, and they're all going to have some distortions associated with them. This equal Earth projection, everything is properly equal area. All the areas are correct on this, but the direction that you would measure on this, the shape of the continents, and the distance from one place to another would not be correct.